All right, we continue in our exploration now of these trigonometric functions, not only trig functions, which you've seen before, but exact values of trig functions for certain angles. And we've already, in previous exercises and videos, looked at how we derive those exact values for, what was it, 30 degrees, 45 degrees, and 60 degrees. And also, I think I touched on 0 and 90 degrees, which don't make sense at all in the context of triangles. But we're going to move forward now and try to make what we know and what we've learned in the past week a little bit more broadly applicable to the idea of trigonometry. Now, before moving forward, you really do have to have a strong sense of these special triangles. My suggestion to you is be able to draw these triangles quickly and efficiently. Do it at the top of every assignment page you get, every test paper you do, and let this be a reference. Now, the more you do this, then the quicker things like sine of 30 equals 1/2 is going to be. And cosine of 30 is root 3 over 2. Okay? The more you do this, the more ingrained this becomes. And that's different than memorization. This is making things automatic. I don't memorize those. I learned to internalize them after drawing many, many dozens of these kinds of triangles for every test, every evaluation, every worksheet I did as a student myself. All right, angles and standard position. Angles and standard position. A couple of bits of terminology now we're going to address. All right. When we're talking about angles moving forward, we're talking about two parts of the graph which create an angle. We're talking about where the line begins, which is along the x-axis, and which we call the initial arm. And if you can imagine that we move this line up and we're sweeping an area here, and we keep going up and up and up and up until we come to the angle that we want, and that there's this arc being formed. Now that doesn't look like a triangle. This sure does. And so where the arm of this shape, let's call it, ends up now is going to be called the terminal arm. So there's an initial arm and there's a terminal arm, which together creates an angle. Now let's go back to something which you may have been wondering about. In previous years, you may have heard of the parts of a Cartesian graph being referred to as quadrants. That's quadrant 1, that's quadrant 2, quadrant 3, and quadrant 4. That's going to become more important moving forward in math. Why is quadrant 1 in the top right corner? Well, if you remember, this is the positive x direction and this is the positive y direction. And similarly, this is the negative x direction and the negative y direction, okay? So it kind of makes sense that quadrant 1 is where everything is positive, okay? And that's the way we sold it to you in past years. But now you know a slightly different story. The reason why quadrant 1 is in this direction is the same reason why this is labeled on maps as east and that is west, is because thousands of years ago, we observed that the sun rises in the east, makes a big arc in the sky, and sets in the west. And so by convention, a convention set thousands of years ago, and based on trigonometry, east is the positive direction. And when we're talking about how the sun moves through the sky, and when we're talking about how angles are formed, it is always going to be in the counterclockwise direction, right? This is counterclockwise. So let's talk about another definition then. Standard position. Standard position. So an angle is in standard position if its initial arm is on the x-axis, not only the x-axis, but the positive x-axis, and the vertex of the angle is at the origin. Positive angles are always rotated counterclockwise from the initial arm, and negative angles, conversely, are rotated clockwise. Angles in standard position can be larger than 360 degrees. Let me show you what I mean there. Can you imagine an angle which is formed by the initial arm right there, going counterclockwise around the origin and stopping there, creating a terminal arm that looks like that? So let's try to add up these angles and figure out what theta we're talking about here. Well, starting here, this first rotation is 90 degrees. If you keep going to there, you've got another 90 degrees. If you keep going here, you've got another 90 degrees. If we keep going to there, we've got another 90 degrees. And finally, if we make this last little bit there, Well, I'm going to tell you that's 45. Okay, I'm just going to lay out, tell you that's 45 degrees. So if we add up all of these bits of this line going all around and ending there, then we have an angle of 90 and 90 and 90 and 90, which is 360, plus 45. We have an angle of 405 degrees. Now, I've also given you a little bit of information. I've told you what that angle is right there, and I've told you that that is 45 degrees. And so what you might appreciate right now is that there's a relationship. There seems to be a relationship between 45 degrees and 405 degrees. And the quick and clever among you might see this right away. So if you see this, give it a try. Figure out what sine 45 is and what sine of 405 is. Make a prediction and see what you got. See if it holds true for cos 45 and cos 405. Put this video on pause and try those out. See what you get. I'll wait. All right, so if you went ahead and did that, you will have noticed something. You will have noticed that sine 45 is what, 0.7071, and that the sine of 405 is the same thing, 7071. So that relationship between 45 and 405 is kind of special. So angles in standard position can be larger than 360, as demonstrated right there. Depending on the size of the angle, of course, the terminal arm could be in any quadrant. It could end up in quadrant 1 as it did here, but you can imagine a situation where it ends up in quadrant 2, quadrant 3, or quadrant 4. And so now the acute angle that's created in every case, regardless of what quadrant you choose to rotate the terminal arm into, the acute angle between the terminal arm and the x-axis seems to be special and seems to be related to that angle there, 45 degrees in this case. So that relationship between that initial angle and an angle that's rotated 360 degrees more, or as you'll learn, 90 degrees more, or 180 degrees more, or 270 degrees more, we call that initial angle the reference angle. The reference angle of an angle in standard position is the acute angle formed by the terminal arm with the x-axis, and it's always stated as a positive angle. Now, we haven't talked about positive and negative angles. Let's do that very quickly here. So if I have an angle that starts here from the initial arm and rotates, say, to here, and I'm just going to say that this is 45 degrees, and I'm interested in what this angle is here. That angle, let's call it theta 1, obviously equals 90 plus 45, which equals to 135 degrees, okay? But I could also take a different angle. I could arrive in the same place by starting here and moving clockwise to the same location, like that. And let's call this theta 2. What would theta 2 be equal to? Well, theta 2 would be equal to 90 degrees plus 90 degrees plus, well, if this is 45 here, then this is also 45 degrees. So it's 90 and 90 and 45 degrees. And when I add those all up, I get 225 degrees. And hopefully if you add those two up, you should get 360 degrees. And we do, which is good because I've done a complete full circle here. And so what this seems to imply is that there's a relationship between the functions of 135 degrees and the functions of negative 225 degrees. And so I invite you to think about this for a moment, pause the video, pull out your calculators, and do some trig calculations. For example, you don't have to stop there, but start with sine of 135 and sine of negative 225. See what you get. I'll pause. You go ahead. So what did you get? That's right, the same numeric value for both of those angles. Isn't that interesting? And if you understood what we've done up to this point, then the rest of what we're going to do is going to be easy peasy. So the reference angle of an angle is an angle in standard position formed as an acute angle between the terminal arm of any angle that you wish to sketch out and draw on a Cartesian coordinate and the x-axis. And it's always a positive angle because we're always going counterclockwise. All right, how do we use this information? Let's do a couple of examples. So for each angle, sketch the angle in standard position and state its reference angle. All right. So 175 degrees. You know where that's going to end up. You know it's going to end up in quadrant 2 because here's 180 degrees and 175 is less. So it's going to be somewhere around here. Now you don't have to be exact, but it's nice to figure stuff out, okay? So starting at the initial arm and rotating counterclockwise, we end up here. We're going to call this 175 degrees. The reference angle is the acute, so the angle less than 90 degrees, formed by the terminal arm and the x-axis. 180 minus 70 is going to be 5 degrees. There you go. That is the reference angle for 175. Now, what does a reference angle mean, and what's it good for? Well, if you go ahead and figure out sine 175 degrees, cosine 175 degrees, and tangent of 175 degrees, and compare it to sine of 5 degrees, cosine of 5 degrees, and tan of 5 degrees, then I think you'll be in for a pleasant surprise. That's the purpose. Because figuring out the tan function values for small angles is sometimes a little bit easier than figuring them out for large angles. All right, let's try this one. 40 degrees. 40 degrees. Well, 40 degrees, this is 45 degrees, so 45 is going to be a little bit less, like that. Let's just label it. We've already gone from the initial arm to the terminal arm. We've rotated in the positive direction, counterclockwise. Theta reference is going to be simply 40 degrees. We have it already. So to figure out negative 120 degrees, we'll start with an initial arm there along the positive x-axis. So starting here, we're going to go 90 degrees and then a little bit more. How much more? Well, we need to go another 30 degrees to make it 120. So we're going to go to about there. All right. That's going to make this angle of negative 120, which is really equal to negative 90 plus negative 30. All right. And now we got to figure out what the reference angle for that will be. Well, the reference angle is measured in a positive direction, so counterclockwise, as an acute angle from the x-axis. This is what we're talking about here, okay? And we'll label that theta r. And so theta r, or the reference angle for negative 120 degrees, is going to be, well, we know that this is 90, so the reference angle is 60 degrees. And that's all there is to it. Reference angle for 90 degrees. Well, how do we get to 90 degrees? We start here at the origin with a initial arm, and we seem to rotate up there, and we end up with the terminal arm up there. Is there any acute angle to refer to compared to 90 degrees? And I mean, you can go that way, but that's not acute. That's 90 degrees. You can go that way, and that's not acute. That's 90 degrees. There doesn't seem to be a reference angle for 90 degrees because there is no acute angle. Well, would you believe that for 90 degrees, or in fact 180 degrees, or 270 degrees, or 0/360 degrees, that these are special cases? And so the word we give these are quadrant angles. And quadrant angles don't have a reference. Let's take a look at 600 degrees. 600, I feel like Austin Powers here. 600 degrees. Well, we start the same way we always do. We're going to start on the terminal arm at the vertex, with the vertex at the origin, and we're simply going to walk around the graph. So let's do this together, and hope I don't get my 90 multiples all messed up. 90 degrees, 180, 270, 360, 450, 540, 630. Uh-oh, okay. So there's 630 degrees, which means for an angle of 600 degrees, I need to be 30 less. So there we go. This is just an angle I'm keeping track of. That happens to be 30 degrees. Let's just verify what we did. Starting from here, I went 90, 180, 270, 360, 450, 540. If that's 60, 540 and 60 would be 600. So this appears to be true. And because I know that this angle is 630 minus 30 to give me the 600, I know that this angle here is 60 degrees. And there's my reference angle. Theta reference is going to be 60 degrees. So what would happen if we rotated another 360 from any angle we choose, okay? Pick any out. Think of any angle. Think 30. And let's say we rotate 360 degrees from 30 to get 390. In other words, let's say we go from 30 degrees to 30 degrees plus 360 degrees, or 390 degrees. Well, whenever you rotate your angle 360 degrees, you come back to the exact same place, okay? So you'll get multiples of angles that are all equal. So you get 30 degrees being equivalent to 390 degrees, right? 360 plus 60, which is going to be equivalent to, at another 360 is going to be 750, okay? And you can do that all day long, and you get your multiples of your initial angle plus 360, and you will always end up in the same place. All right, so this idea of ending up in the same place, all right, well, guess what? That has a word as well, and that is called coterminal angle. Coterminal angle. Angles in standard position that have a common terminal arm. For example, 30 degrees and 390 and 750. For example, 60 degrees and 420 degrees. See how that works? So let's investigate this situation a little bit. Let's take an angle of 300 degrees. Well, we know that it's going to be in quadrant 4 somewhere, because this is 270 degrees and this is 360. Well, this is 0 or 360 degrees. So we know the line is going to, the terminal arm is going to be in quadrant 4 somewhere. Where exactly? Well, here's 90, 180, 270. Looks like I need an extra 30 degrees. So 30 degrees does it there. There's my angle of 300 degrees. And now we got to figure out a coterminal angle with 300 degrees. Well, all I got to do is go plus 360, like that, and I'm going to have that angle. And that angle is going to be 300 plus 360, which is 660 degrees. I could go another 360 degrees. Then I get 660 plus 360 equals 1020. And I can do that all day long. Those are all coterminal angles. 300, 660, 1020, all coterminal angles. And so if I want to summarize a formula for determining coterminal angles, then I might say that any coterminal angle can be calculated by taking the initial angle and adding 360n. That is 360 degrees times n, where n is a member of the integers. As long as I multiply by whole portions of 360, then I'm going to get coterminal angles. All right, here's your work. Practice questions beginning on page 237. Whole bunch of them. Question 3, 4, 5. Moving on to the next page. 6, 7, 8. And the next video, we'll talk about new definitions of trigonometric ratios. Happy mathing.